Hey everyone, welcome to this explainer. I'm really glad you could join me today. Before we jump in, just take a comfortable seat, take a deep breath, and let's get ready to explore a fascinating, completely invisible world that is literally surrounding us every single day. Today, we're looking at the unseen chemistry of water. And hey, I know these concepts might seem a little complex at first glance, but I promise you, they are entirely logical once we break them down together.
Okay, let's kick things off with a scenario you've probably actually experienced yourself. Have you ever traveled to a new city, hopped in the shower, and suddenly noticed that your regular soap just absolutely refuses to lather? Like, instead of getting all nice and sudsy, it just leaves your skin feeling strangely dry, and maybe there's even this weird sticky film left on the bathtub? Well, it's actually a super common experience, and it happens to be our very first clue into the hidden chemistry we're unpacking today.
So what you're dealing with in that shower is what chemists call the hardness of water. Hardness is simply a characteristic property of water that prevents the lathering of soap. In fact, back in the day, it was literally just defined by its soap-consuming capacity. It's a very tangible, everyday physical phenomenon. Basically, if water forms a soft, creamy lather, we call it soft water. But if it forms a sticky, curd-like residue, yep, you guessed it, we call it hard water.
But why does this even happen? Well, water is often called the universal solvent. Think about a raindrop falling from the sky. It starts out relatively pure, right? But as that water travels for miles and miles over rocks and filters deep down through the soil to reach underground aquifers, it acts kind of like a magnet. Through dissolution, it picks up these invisible mineral hitchhikers along its journey. Now, mostly these are dissolved calcium and magnesium ions. And here's the kicker. Because they are fully dissolved in the water, you can't just filter them out with a simple physical sieve.
Now, normally soap is fantastic at its job. It's got this sodium end that loves water and a fatty end that loves oil, which lets it mix the two together and wash away dirt. But when calcium and magnesium are hanging out in the water, they are highly reactive. They swoop right in, outcompeting and actually replacing the sodium ions in your soap. The result? The soap molecules bind with the calcium and magnesium to form this insoluble white, curdy precipitate. That is the sticky scum you're seeing. Those minerals are quite literally stealing your soap.
Not all hardness is created equal, though. Chemists essentially divide this whole phenomenon into two camps. First up, we have temporary hardness. This one is caused by bicarbonates of calcium and magnesium. The really convenient thing about temporary hardness is that you can easily defeat it just by boiling the water. The heat just breaks it down and the minerals safely settle right to the bottom of the pot. But then, we have permanent hardness. This is caused by chlorides and sulfates of those exact same metals. And let me tell you, boiling does absolutely nothing to permanent hardness. To get rid of it, you actually have to bring in chemical softening agents using things like the lime soda or ion exchange processes.
So, you might be wondering, what does this all mean? Why does any of this matter outside of a college chemistry lab? Well, at home, hard water gives a scratchy, harsh laundry because that soap curd literally sticks to the fabric fibers. It leaves our hair feeling greasy and lifeless, and it leaves those annoying white spots all over our dishes. But on an industrial scale, it's a massive hazard. When hard water is heated in massive boilers, those minerals precipitate out and form thick limescale deposits right on the machinery. This scale acts as an unwanted insulator. And get this can waste up to 25% of heating energy. Even worse, it can cause the pipes to completely clog or the boilers to overheat and catastrophically fail. So yeah, mastering this chemistry is absolutely crucial for our infrastructure.
Section 2. The color-changing puzzle, complexometric titration with EDTA. Now, since we know exactly how important it is to control water hardness, we need a really precise way to measure it in the lab. Picture this. You've got a glass flask filled with our hard water sample. Step 1, we add a specific ammonia buffer. This is basically just setting the stage, keeping the water perfectly stable at a pH of around 10. Next, we drop in our chemical spy, an indicator dye called Eriochrome Black-T, or EBT for short. As soon as that EBT hits the water, it grabs onto the free calcium and magnesium ions, and the water immediately turns this beautiful, deep wine-red color. Finally, step 3, we slowly drip in EDTA. And when the job is done, the water shifts entirely to a clear sky blue. Let's zoom in on that EDTA for a second. It works through a process called chelation, which is just a fancy way of saying it functions kind of like a tiny, highly efficient molecular claw. When we drip it into that wine-red water, this claw reaches right in and starts safely trapping the calcium and magnesium ions, forming highly stable, totally colorless complexes with them. Now, remember our indicator dye, EBT? It was holding on to some of the calcium and magnesium, right? Which is what made the water wine red in the first place. But that EDTA claw, it's much stronger. Once the EDTA has trapped all the free-floating metals, it marches right over to the EBT indicator and plucks away those last remaining metal ions. With the metals finally gone, the EBT indicator is set free, and in its free unbound state, EBT naturally has this peaceful clear blue color. So, the exact moment the water flashes from wine red to clear blue, we know for a fact the EDTA claw has caught every single hardness-causing ion. From there, we just measure how much EDTA we used, and boom, we've solved the puzzle.
Okay, take a breath. We've just navigated some really cool physical-chemical reactions, where a simple color shift tells us exactly what's happening on a molecular level. Now, let's smoothly transition into how chemists translate that visual puzzle into standard math on paper. And I promise you, it is just as elegant and low pressure as the color change we just watched.
The key to literally all the math regarding water hardness comes down to this one beautifully round number, 100. This happens to be the exact molecular weight of calcium carbonate. Now you might be wondering, why calcium carbonate? After all, we just learned water hardness is caused by a whole bunch of different salts: magnesium sulfate, calcium chloride, magnesium bicarbonate. If you tried to calculate them all individually, the math would be an absolute nightmare. So chemists made a brilliant simplifying decision. They decided to convert every single type of hardness into the equivalent of just one standard salt, calcium carbonate. They chose it because, well, its molecular weight is exactly 100, which makes the math incredibly easy for us. Plus, it's the most insoluble salt that precipitates out of water, making it just a perfect baseline standard.
And that brings us to the equivalence formula. To find the calcium carbonate equivalent, all you do is take the amount of the hardness-causing salt you actually found in the water and multiply it by 100 divided by the molecular weight of that specific salt. It's essentially just a matching game, a straightforward conversion factor to put everything onto the exact same scale.
To see how cleanly this works in practice, let's say our lab analysis finds 14.6 milligrams per liter of magnesium bicarbonate. Now, the molecular weight of magnesium bicarbonate just happens to be 146, so we plug it right into our formula. We take our 14.6 milligrams and we multiply it by our factor of 100 over 146. Because the numbers are chosen so well, 14.6 neatly reduces down to a perfectly clean 10 milligrams per liter of calcium carbonate equivalent. See? No stress, no complex calculus, just straightforward logic.
As we bring this explainer to a close, let's ground ourselves right back in the physical reality of what we've learned, using this quote directly from our source material. The hardness of water is defined as the property which prevents the lathering of soap. We've traveled all the way from a frustrating shower in a new city, down to the molecular level of bouncing ions, to the specific color shift of a lab titration, and finally to the simple elegance of the number 100. But it all comes back to this tangible, everyday, real-world experience.
By just taking the time to slowly and calmly understand these hidden chemical interactions, how water picks up minerals, and how we can effectively measure and manage them, we are so much better equipped to protect our homes, our industries, and honestly, just live comfortably and safely in our world. So it makes you think, what other invisible interactions do you think are happening around you right now, just waiting to be understood? Thank you so much for joining me on this explainer, and keep exploring.